In the next section, we'll be looking at lipid digestion and the important role played by bile in this process as well. In this section of the GI physiology module, we'll be looking at bile, bile salts, and lipid digestion. The first diagram shows a cross-section of the liver. In this cross-section, you can see the architecture of the liver with a central vein, a branch of the portal vein, and hepatic artery which run together. There are also bile capillaries present, which then will drain into biliary canaliculi and then into the intrahepatic bile ducts. Hepatocytes secrete bile into hepatic bile ducts. Bile is made up of bile salts, bile pigment, cholesterol, phospholipid, ions, and water. The gallbladder is responsible for concentrating bile, and it does so by up to 15 times. Bile salts are very important in digestion because they emulsify fat and form micelles around lipid digestion products. The phospholipids and cholesterol that are present in bile participate in micelle formation. Cholecystokinin, as we discussed earlier, contracts the gallbladder and relaxes the sphincter of Oddi. This means that bile can travel out of the gallbladder into the small bowel. Before bile acids leave the liver, they are conjugated. So primary bile acids are cholic acid and chenodeoxycholic acid. These are conjugated to an amino acid, glycine or taurine, to form one of 8 bile salts. Intestinal bacteria remove these from primary bile salts, and primary bile acids are then converted to secondary bile acids by removing a hydroxyl group. So the primary bile acids are represented by cholic acid and chenodeoxycholic acid. After encountering intestinal bacteria and removal of hydroxyl groups, they are deoxyhydrocholic acid and lithocholic acid. So as shown in the last diagram, hepatocytes secrete 2 primary bile acids, cholic acid and chenodeoxycholic acid. When they're secreted into the lumen of the intestine, they're dehydroxylated by intestinal bacteria, and we get the secondary bile acids, deoxycholic acid and lithocholic acid. The liver conjugates the bile acids with an amino acid, either glycine or taurine, to form bile salts. Consequently, there are a total of 8 bile salts, and these are named by the parent bile acid and the conjugating amino acid. So, for example, if the parent bile acid is cholic acid and the conjugating amino acid is glycine, it's called glycocholic acid. Or if the conjugating amino acid is taurine, it's named taurocholic acid. With this conjugation step, the pK of the bile acids has changed and they become much more water soluble. This becomes important because bile salts, if they are water insoluble, cannot do their job with micellarization. So the pH of the duodenum content ranges between 3 and 5. Bile acids have a pK of approximately 7. Thus, at a pH of between 3 and 5, most bile acids are in their non-ionized form. This means that they are insoluble in water. If bile salts have a pK between 1 and 4, this means that a duodenal pH of between 3 and 5, most bile salts will be in their ionized form. In this form, they are soluble in water, and therefore bile salts are much more soluble than bile acids in the aqueous duodenal contents. So just to recap, conjugation with amino acids changes bile acids into bile salts. This is important because when bile is released into the duodenum is primarily aqueous. Because it's aqueous, these bile salts will be soluble with their lower pKs. The bile acids, on the other hand, which are unconjugated, will be insoluble, as this is predominantly an aqueous environment, and so bile salts work much more effectively than bile acids in this aqueous environment. It's important to remember that only 5 to 10% of bile salts are excreted in the feces. Therefore, up to 90% are resorbed so that they may be reused. And bile acid pool may recirculate several times during the digestion of a meal. Clinically, this is relevant in scenarios where enterohepatic circulation cannot take place, such as in Crohn's disease, where there's terminal ileal disease. There is negative feedback on one of the synthetic enzymes by the bile salts, cholesterol 7-alpha hydroxylase, which regulates synthesis. Therefore, the rate of synthesis of new bile acids is inversely proportional to the return of bile acids. Hence, if there's increased return of bile acids, there's decreased rate of synthesis and decreased activity of cholesterol 7-alpha hydroxylase. As I mentioned earlier, bile acids are resorbed in the terminal ileum by the sodium bile salt cotransporters. Any reason for this to be abnormal, such as in Crohn's disease, which often affects the terminal ileum, or in TB, can result in malabsorption syndromes. Bile also contains pigments. Bilirubin, which gives stool its color, is the breakdown product of heme. Hepatocytes pick up bilirubin from the bloodstream and conjugate it with glucuronic acid. The conjugated bilirubin, or bilirubin glucuronide, is secreted into the intestinal lumen. The GI bacteria convert bilirubin to urobilinogen, and then urobilinogen can undergo a number of different things. It can be resorbed into the blood and secretion by the liver into bile. It can be resorbed into blood and excreted in urine. Oxidation to urobilin and stercobilin can occur, and these are the dark pigments that give feces its color, and they are excreted with stool. Therefore, any cause of obstruction in the gallbladder, for example, if bilirubin cannot be secreted into the intestinal lumen, can result in dark urine and pale stool. There is pale stool because bilirubin is not excreted, and oxidation to urobilin and stercobilin does not take place, and excretion with stool does not take place. There is, however, resorption into blood still occurring of urobilinogen and is excreted by the kidneys, resulting in dark urine. Lipid digestion and absorption takes place all along the GI tract. We have mentioned in lecture 1 that lingual lipase is present, and it hydrolyzes triglycerides to fatty acids plus 1,2-diacyl glycerols. In the stomach, there's also another lipase called, unsurprisingly, gastric lipase, and it hydrolyzes triglycerides to glycerol and fatty acids. Pancreatic lipase hydrolyzes triglycerides to fatty acids and monoglycerides. Colipase facilitates the exposure of the active site of pancreatic lipase. There's also cholesterol ester hydrolase, which hydrolyzes cholesterol esters to cholesterol and free fatty acids. And phospholipase A2 hydrolyzes phospholipids into lysolectin and free fatty acids. Unfortunately, this is a list of enzymes, the first three of which you should be familiar with, and the last three which may be tested upon and you just have to memorize. Bile acids tend to form micelles and form when the concentration of bile acids exceeds a certain limit. This is known as the critical micelle concentration. So what this means is that if there are enough bile acids present, they will automatically form a micelle. These micelles will contain products of lipid digestion, namely fatty acids, monoglycerides, lysolectin, cholesterol, and fat-soluble vitamins A, D, E, and K. And this product is delivered to the enterocytes, or the cells of the small intestine. Within the enterocyte, these products are re-esterified. In conjunction with cholesterol esters, phospholipids, and apoprotein B, these form chylomicrons. Chylomicrons are then packaged into secretory vesicles and secreted by exocytosis into the lacteals. They then reach the bloodstream via the thoracic duct. So the next diagram just shows an overview of what happens with absorption of lipids. Number 1, products of lipid digestion, namely the cholesterols, monoglycerides, lysolectin, and free fatty acids, are solubilized in the intestinal lumen in mixed micelles. These micelles are present because of the presence of bile salts, and which are present at a limit beyond which critical micelle concentration takes place. The micelles will then diffuse over to the apical brush border of the intestinal epithelial cells. Here, as I mentioned, the products of lipid digestion are re-esterified with free fatty acids. They are then packaged with apoproteins in lipid-carrying particles called chylomicrons. Chylomicrons have phospholipids which cover 80% of the outside surface, and the rest, or 20%, is covered by apoproteins. Apoproteins are synthesized in the intestinal epithelial cells themselves and are essential for absorption of chylomicrons. If apoprotein B is not synthesized, then a condition called A-beta lipoproteinemia is present. A person is therefore unable to absorb chylomicrons, and dietary lipids cannot be absorbed. This is because there is impaired exocytosis. The chylomicrons are packaged in secretory vesicles in the Golgi apparatus. They migrate to the basolateral membranes, and there is exocytosis of the chylomicrons. They're too large to enter vascular capillaries, and therefore enter the lymphatic capillaries, or lacteals, and enter the lymphatic circulation, where they enter back into the bloodstream via the thoracic duct. This whole process of absorption of lipids is something that is clinically relevant, such as in conditions like A-beta lipoproteinemia, and easily tested. Therefore, steatorrhea can be caused by a number of different disorders. Pancreatic insufficiency, mostly due to lipase deficiency, as fats cannot be absorbed. If there's an absence of bicarbonate, there's a relatively acid milieu in the duodenum, precipitating some bile salts. When this precipitation takes place, micelle formation cannot take place and malabsorption occurs. Zollinger-Ellison syndrome results in excess acid production, and this cannot be fully neutralized by pancreatic bicarbonate. This results in an inactivation of pancreatic lipase, and malabsorption then occurs. Bile salt deficiency as a result of ileal resection or defective resorption or bacterial overgrowth in the terminal ileum results in decreased bile salts, decreased micelle formation, a decreased lipid absorption, and therefore steatorrhea. If there are decreased enterocytes, such as in tropical sprue, where blunting of the villi can occur, malabsorption is also present, and therefore steatorrhea is present. In the last section, we looked at lipid digestion in the GI tract, as well as clinically relevant disorders which present with steatorrhea.